Okay, here's an example. A pulley problem with energy methods. Okay, let's set up the system. We have this composite pulley with two different radii. Okay, it's a single rigid body. Composite pulley with a single rigid body. With two different radii, and what we have are these masses hanging from the two sides of the pulley. Let's call this mass M1, and let's call this mass M2. So they are connected to two different radii. So this radius is let's say R2, and this radius, let's say, is R1. And we have masses M1 and M2, and the mass of this pulley is M3. Okay, pulley mass is M3. So all this is given, and you are asked to find the following thing. Let's say, in addition, that the pulley is a uniform disk. Of radius R1, which means that its Ig is M3 R1 squared by 2. That's what the formula for Ig is for uniform disks. Now, the question asks for the following thing. Say the system starts at rest. Then determine the angular velocity omega of the pulley when mass M1 has descended by height h. Okay, so and the instruction, let's say, is use the energy methods. Okay, for energy methods, of course, you always start with this key equation. Kinetic energy initial plus potential energy initial plus work by other forces equals kinetic energy final plus potential energy final. By other forces, we mean not gravity or springs. Okay. Okay, so that's the main equation. What is the kinetic energy initial? It's of course equal to 0 because you're starting at rest. Let's say the potential energy 0 initial equals 0 as well. This is what we choose to be the datum. What is potential energy final? We will get to that. let's now write an expression for kinetic energy um, final. Okay, so kinetic energy final. Um, let's define some notation here. Let's say the velocity of this mass is v1 going downwards. Let's say the velocity of this mass going upward is v2, and let's say the angular velocity of the pulley is omega, and let's call this v2 final, omega final, and so on, right? So, but final will drop from here. Let's just, so that's the notation that we are creating, or sign convention. Once you have the sign convention, we can say mass m1 is moving at velocity v1, so the kinetic energy for that is half m1 v1 final square plus similarly half m2 v2 final square, plus we also need to add the kinetic energy of the pulley itself. The kinetic energy of the pulley is half I g, its own g, omega square. Okay, that's the kinetic energy final. So let's call this equation 1, 2, 3, maybe call this 4. Okay. Now we have a whole bunch of unknowns here. We are asked to find omega, but we do not know the velocity of mass 2. We do not know the velocity of mass 1. But we've been told, I guess I should have said it explicitly, for all these pulley problems, we will usually make the assumption, and we will state the assumption that no slip between pulley and rope. Okay. So if there's no slip between the pulley and the rope, then this velocity, if we have some point, let's call this point P1 and this point P2, then because this pulley is a rigid body, then the velocity of P1 is just going to be R2. Let's call this, I guess, let me call this P2 and P1 respectively, just to keep it consistent. So the velocity of point P2 is basically R2 omega. Velocity of point P1 is R1 omega. And because there is no slip between the rope and the pulley, the velocity of point P1 will be equal to the velocity of M1. Okay, so let me just write this first. In 4, can we replace V1F and V2F in terms of omega? And the answer is yes. Okay. First, we want to say P1, VP1, V1 equals, right? So V1 is VP1 equals R1 times omega 1. Omega. Basically, we said this is because no slip, and this is because P1 on rigid body. Okay. Similarly, so we can replace V1 in terms of omega. Similarly, we have V2 equals Vp2 equals R2 omega. So let's call this 5. Let's call this 6. Let's plug in 5 and 6 into 4 so that the equation 4 just becomes in terms of omega. So Ke final gets sort of revamped into this relationship. V1 final is basically going to be, V1 is R1 omega, so V1 final is going to be R1 omega final square plus half M2 R2 omega final square plus half Ig omega square, and Ig is M3 R1 square by 2 omega final square. Okay, so we can combine terms here. Half omega final square times M1 plus M1 R1 square plus M2 R2 square plus M3 R1 square by 2. Okay, so that's the kinetic energy final expression. We've reduced it to just one unknown here so far. Okay, let's call this equation 5 for kinetic energy final. What else do we have? We have work done by other forces. Work by other forces will be equal to 0 because what are the other forces? Well, there are things like normal reaction between rope and pulley, friction between rope and pulley. All those forces do exactly 0 work because there is no slip between the rope and the pulley. Because there is no slip, there is no relative motion. Work relies on relative motion between objects or between the force and so the work done by other forces equals 0. What else do we have? We only have potential energy final to be sort of computed. So let's look at that. It's again a slightly subtle thing. Potential energy final equals m1g. We picked the initial position of mass m1 as its own datum, and it's going down by h. So basically y1 final, and then you can say m2 g y2 final measured from where it started. Let's say, and so this is going to be m1 g times minus h. Okay, that's going to be y1 final. What is y2 final? So let's look at this picture again. If m1 goes down by h, how much does m2 go up by? Now, you might be tempted to say h, but that is not the case. If m2 was attached, because they are on two different ropes, m2 is attached to this radius and m1 is attached to this radius. And they're not on the same rope, so they don't go up and down by the same amounts. But we have a clue here. We have a clue here which says V1 is R1 omega, V2 is R2 omega. V1 and V2 are essentially the velocities of M1 and M2. So what is Y2F from measured from its own initial position, right? Initial position. So we just noted M1 goes down by h, that's given. Okay, v1, as we showed earlier, is r1 omega. Velocity of 2, v2 is r2 omega. We can sort of show use these two things to show that v2 by v1 equals r2 by r1, or v2 equals r2 by r1 v1. What does this mean? This means that the velocity of mass 2 is this ratio times the velocity of mass 1, which means that the displacement of these guys are also in the same proportion. Okay, so what we would get is y2f so let me just write it in words first. If mass m1 goes down by h, m2 goes up by h times r2 divided by r1 based on this relationship. So basically your y2 final equals h times r2 by r1. Okay, so we can plug that into this relationship. So P final equals m1g minus h plus m2g. It goes up, mass m2 goes up, so we have a plus here. Okay, so that's P final. Now we have all the relationships that we need. Let's plug in 5, 6, I don't know, I can call this 7 perhaps, 2 and 3 into 1. Into 1, and what we have, K initial is 0, P initial is 0, work done is 0, equals mg minus h plus m2g h r2 by r1. Let me actually write this on the next page. K initial is 0, P initial is 0, work done is 0, and then the potential energy final is m1g minus h plus m2g h r2 by r1. Right? And then the kinetic energy final is half omega square m1 r1 square plus m2 r2 square plus m3 r1 square by 2. And that's it, we are done. In this expression, we essentially are given everything except omega, we can basically solve for omega in terms of everything else. So that's it. Let's simplify ever so slightly. So we have half omega square equals, bringing this to the other side, we have m1gh minus m2gh r2 divided by r1 whole divided by m1 r1 square plus m2 r2 square plus m3 r1 square divided by 2. And that's it. We can simplify further, I suppose, if we wanted. Omega equals square root of this whole thing. There's a 2 in the numerator now because this 2 goes up, and then you can pull this in the denominator, same thing as before. Oops. That's in the denominator, and that's going to be the final answer, okay? That's going to be your answer. And that's it. So it was just, in some sense, straightforward application of this equation, except we had to use things like no slip to find relationships between angular velocity and linear velocity, so that you had enough equations and unknowns, so that this one equation was sufficient to solve for everything. So because of no slip, V2 was basically R2 omega and V1 was R1 omega. And that helped us simplify KE final. Similarly, we could represent, if we were told that this went down by H, and we could use the same sort of no slip condition, the fact that these velocities are related by the radius ratio, to actually find how much this went up by, which is not equal to H, but actually H multiplied by some kind of a radius ratio. Okay, like so. So, and then that allowed us to solve for the final expression for omega. I guess we'll stop there.